Now we'll come to the different concepts of acids and bases. Different concept. Now this you have read it in lower classes also, a little bit about it. That acids are those substances which are sour in taste, and bases are those substances which are bitter in taste. We can say that. Because we have also studied acids are those substances which gives H plus ion in aqueous solution. You have also studied acids are those substances which turns blue litmus red, methyl orange, pink, phenolphthalein colorless. All this you have studied. Alright, clear. All this you have studied in the lower classes. So different, what you can say, people from time to time they have given some different concepts regarding acids and bases. Alright, now these are the classical concepts which I was saying just now to you. Now acids are those substances which gives H plus ions in aqueous solution. Is the concept given by Arrhenius. We can say that. Arrhenius concept. Arrhenius. We can say Arrhenius concept of acids and bases. Arrhenius gave us this particular concept. Now what Arrhenius said us? Arrhenius said that acids are those substances which gives H plus ion as the only positively ion, or H3O plus ion, hydronium ion, as the only positively charged ions in aqueous solution. They are called as an acid. Like HCl dissolves in water, H2SO4 dissolves in water, HNO3 dissolves in water. Alright, they gives H plus ion, or we can say thermodynamically H3O plus ion, I should say that, because H plus ion when reacts with the water, it forms H3O plus ion, which is quite stable compared to H plus ion. Alright, rather H3O plus ion is stabilized by resonance. H plus ion does not show resonance, we can say that. So in this way, what we find is that H3O plus ion, it gives in aqueous solution as the only positively charged ion, that is called as an acid. Similarly, according to Arrhenius, bases are those substances which gives OH minus ion as the only negatively charged ion in aqueous solution. As the only negatively charged ion in aqueous solution, that is called as a base, we can say that. Like NaOH, it gives Na plus plus OH minus. KOH, it gives you K plus plus OH minus. Ammonium hydroxide will give you NH4 plus plus OH minus, we can say that. So in this way, acids are those substances which gives H plus ions in aqueous solution as the only positively charged ion. Bases are those substances which gives OH minus ions in aqueous solution as the only negatively charged ion. They are called as an acids and bases, we can say that. But there are certain limitations also. There are certain limitations. Now, you know that weak acids will dissociate feebly. They will give less concentration of H plus ions. Similarly, weak bases also will dissociate feebly. They will give less concentration of OH minus ions. So, should we call those particular substances acids and bases? Yes. What I said you? Arrhenius said large concentration. So, this is another one drawback, we can say that, because they give small concentration of H plus and OH minus ions. Isn't it? Clear? So, in this way, according to Arrhenius, they may or may not be considered as an acid or a base, we can say that. What my point? Now, next is, after that, so hence, we need to, what we can have to do is that, Arrhenius, what he need to do is that, he need to classify it, that this is a strong acid which gives H plus ion, more of H plus ions. And if it is a weak acid, it will give you less concentration of H plus ions. H plus ions, we can say that. Similarly, for a base also, if it's a strong base, it will give you more concentration of OH minus ion. If it's a weak base, it will give you less concentration of OH minus ions. So Arrhenius need to classify, has to classify in this particular manner, but he did not do so, Arrhenius. We can say that. Clear? Fine. So now, next is, it is not necessary that all the acids should dissolve in water. There are many acids are there which are not mineral acids, like organic acids. They are not soluble in water, but they give H plus ions, and they are acidic in nature. They are acidic in nature, like formic acid. It is not soluble in water. We can say that. Vinegar, acetic acid soluble in water. Formic acid, propionic acid, malic acid, lactic acid. Alright, they are not soluble in water. We can say that. So those acids, what we can say, are they not acids then? Is it not an acid? Of course it's an acid. But according to Arrhenius, it is not an acid because it is not soluble in water. It does not give H plus ions in its aqueous solution. So that is the drawback, one of the drawback of what you can say Arrhenius concept. According to Arrhenius, what you find is that he says that an acid and base undergoes, that is reacts with each other to form a neutralization reaction. That is, it forms a salt and it undergoes a neutralization reaction. But how it undergoes, he did not explain anything about it. He did not explain anything about it. Now today we know it, that H plus plus OH minus gives you water, and hence it undergoes nucleation. But simply gave a statement that H plus when reacts with when acid and base reacts, they form salt and water, and hence this reaction is called as a nucleation reaction. But how it neutralizes, that fact was not given by Arrhenius. That was not explained by Arrhenius clearly. We can say that from the lower classes we studied. So on based upon our previous knowledge, we are saying you that H plus plus OH minus is give you water. But this was not clarified clearly by Arrhenius. Mind it. Fine. Now next is there are many what you can say acids and bases which are acidic in nature, like sulfur dioxide, carbon dioxide are acidic gases. They are acidic gases. How can we say these acidic gases? According to Arrhenius, they do not give H plus ion. Then how we can say acidic gases? From our previous knowledge, got it? We can say that as it dissolves in water to give carbonic acid, like HCO2 dissolves in water to give carbonic acid. Carbonic acid dissociates feebly to form H plus and CO3 2 minus. Hence, it is an acid. Got it? But it was not explained by Arrhenius, because Arrhenius very clearly said that that is the substance which dissolves in water to give H plus and OH minus ion. They are considered to be as acids and bases. That too in large quantities. It should be. Got it? So, however, a number of substances like ammonia, sodium carbonate, calcium oxide, they are basic but do not contain any hydroxyl group. They do not contain. Similarly, there are a number of substances like told you CO2, SO2, SO3, etc. are supposed to be acidic, but they do not contain any H plus ion. So these are the limitations of the Arrhenius concept. So after Arrhenius comes the Bronsted-Lowry's concept. Bronsted-Lowry. This is the first one. Second one is your Bronsted-Lowry's concept of acids and bases. According to Bronsted-Lowry, that is an acid is a proton donor and a base is a proton acceptor. Alright, now it becomes a little bit wider. In Arrhenius, whatever the substances which was not included in acids and bases, in Bronsted-Lowry, those substances got the what you can say list in acids and bases. Alright, it was being added to the list of acids and bases in Bronsted-Lowry's concept. We can say that those substances which was not included in Arrhenius concept. So what I said, that is acid is a proton donor and base is a proton acceptor. Now look here, HCl, you know it's an acid. How we can say according to Bronsted-Lowry? Because it gives H plus and Cl minus. See, it gives you H plus ion. So it is an acid. It is an acid, we can say that. Clear? Now next is ammonia. It's a base, we know that. It takes H plus ions and it gives you NH4 plus. So acid is a proton donor, a base is a proton acceptor. A base is a proton acceptor, we can say that. The one which accepts a base is called as a one which accepts an H plus ion is called as a base according to Bronsted-Lowry, we can say that. Clear? So hence we have got a conjugate acid base pair in what you can say in Bronsted-Lowry's concept. What is that? That is conjugate acid base pair, I said. That is conjugate acid. This is a conjugate base. You can say this is a conjugate base and H. What if we are having H plus ion? This is a conjugate acid. This is a conjugate base and this is an H plus ion. So I mean to say that if you add an H plus ion to a conjugate base, you will get a conjugate acid. Or if you want a conjugate base, then you remove an H plus ion from conjugate acid. Listen carefully. If you want conjugate base, then you bring H plus ion this side, it becomes minus. So if you remove a H plus ion from conjugate acid, you will be getting a conjugate base. If you want a conjugate acid, then you add an H plus ion to conjugate base, you will get a conjugate acid. So everything is the H plus ion. If you add an H plus ion to a base, you will get an acid. If you remove an H plus ion from an acid, you will get a base. We can say that. So hence we get a conjugate acid base pair. We got it in what you can say in Bronsted-Lowry's concept. But in Bronsted-Lowry's concept, what you find is that water is amphiprotic in nature. We can say that, or amphiprotic in nature. What do you mean by that? Water acts both as acids as well as a base. Now this creates a confusion. Alright, you know that water is neutral in nature, neither it is acidic nor basic. But according to Bronsted-Lowry, water can act as both acids as well as with bases, as well as like bases. So hence it is amphiprotic, A-M-P-H-I, P-R-O-T-I-C, P-R-O-T-I-C, that is amphiprotic in nature. We can say that. Or which is otherwise called as amphoteric in nature also, we can say that, which has come from the word amphoteric, amphiprotic. Okay, so how can we say that water can act both as acids as well as with bases? How it is amphiprotic? See here, now HCl reacts with water to form H3O plus Cl minus. Now you know this is acid 1 and this is nothing but base 1, because this acid dissociates to give you the corresponding, what you can say, base. We get it. This is the conjugate acid, this is a conjugate base. Fine. Now, next is, what you find is that this H2O, it gains H plus ion, gains to form H3O plus. So, base is a proton acceptor. So, hence this is what? Base 2. And this is nothing but is your acid 2. Because H2O, how it forms H3O plus? How it forms? H2O forms H3O plus. How? By gaining H plus ion. So when you gain, when a substance gains H plus ion, according to Bronsted-Lowry, it is what? A base. So here you see water acts as a base. Fine. Now ammonia plus water, it forms what? NH4 plus OH minus. You know ammonia is a base. Let us say it's a base 1. Alright. Now what you find is that it gives you ammonium ion. So it is nothing but an acid. It's an acid. Ammonia gains H plus ion to form ammonium ion. It gains. It's a base. Now, water loses H plus ion to form OH minus. Water gives H plus and OH minus, loses. So, an acid is a proton donor. Alright, it loses. It's a donor. So, this is your acid 2. So, this is your base 2. We can say that. Clear? That means here this is the conjugate acid of this, and this is the conjugate base of this particular acid. For that reason I have written clearly acid 1 base 1, acid 2 base 2. Means this is a conjugate, this is the acid, and this is its conjugate base. Now this is the acid, this is its conjugate base. Fine. So here water acts as a base, here water acts as an acid. So hence it is amphiprotic in nature. This is also, you can say, one of the drawback of Bronsted-Lowry's concept, where Bronsted-Lowry has said water is amphiprotic, but we know that water is neutral in nature. Water is neither acidic nor basic, it is neutral. Got it? So Bronsted-Lowry's concept, if you see the advantages, what is the advantages of Bronsted-Lowry's concept over Arrhenius concept? Got it? If you see, then Bronsted-Lowry's concept is not limited to molecules, but includes, we can say, even the ionic species which acts as acids or bases. As you can see in front of you, it includes ionic species. It can explain the acid-base reactions in the non-aqueous medium also, it can say that, or even in the absence of solvent. Clear? Like between HCl and ammonia, as you can see there in front of you, it is being there. Clear? Now it can explain the basic character of substances like Na2CO3, ammonia, etc. It can explain the basic character as well as the acidic character of also certain substances, which was not explained by Arrhenius. Which was not explained by Arrhenius, we can say that. Clear? But the limitation of this concept is that it cannot explain the reaction between acidic oxides like carbon dioxide, sulfur dioxide, sulfur trioxide, etc. It could not explain the reactions. Or it could not say. Have I said you about carbon dioxide, sulfur trioxide? No, nothing. And basic oxides like calcium oxide, beryllium oxide, magnesium oxide, it could not say the reactions. That how these are basic and how CO2, SO2, SO3 are acidic in nature. Bronsted-Lowry could not say anything about it. Now, substances like BF3, AlCl3 do not have hydrogen. They do not have hydrogen, and hence they cannot give a proton. But it is acidic in nature. Got it? It behaves as a what you can say acidic substance. AlCl3 behaves as an acidic substance. BF3 behaves as an acidic substance. AlCl3 behaves as an acidic substance. AlBr3 behaves as an acidic substance. But it does not have H plus ions. It is not a proton donor. Then how it is acidic in nature? He could not explain. Who? Bronsted-Lowry could not explain anything about this particular substances. So the next concept came is your Lewis concept. Lewis. So Lewis, what he said? Lewis said that an acid is a substance which is capable of accepting a pair of electrons, and a base is a substance which is capable of donating a pair of electrons. So you can say that. So an acid is an electron pair acceptor and a base is an electron pair donor. Got it? An acid is an electron pair acceptor and a base is an electron pair donor. Again I repeat, according to Lewis, an acid is a pair of electron acceptor and a base is a pair of electron donor. We can say that. So if you use this particular concept, you will see that lot of substances comes under acids and bases. Lot of substances. Rather, the chemistry is divided into two. One is your a pair of electron donor, other is a pair of electron acceptor. Means a part of the organic chemistry is acids and the remaining part is bases. Means there is no neutral substances in it. So this is the drawback of the Lewis concept, we can say that. Now, but after Lewis concept, we don't have any other concept. So hence we are considering the Lewis concept to be as correct. But it has also got certain drawbacks. But if you get tomorrow some other concept apart from Lewis, then we can say that this is a drawback of the Lewis concept. Got it? We can read about it. But now for the time being, no other concept has come up. Got it? Apart from the Lewis concept. Got it? No other concept. So just I said you this one because for a beginner, the person who is studying chemistry in class 6 and 7, if I say to that particular person that acid is a pair of electron donor, acceptor and a base is a pair of electron donor, then what he will understand? He will not understand anything at all. Nothing. So to him I have to explain an acid which has sour in taste, acid which turns blue it must red, and acid which gives H+ ion. For the beginners I have to use this particular concept. But for the people like you who is studying in class 11, 12, they can understand it because they have already studied the fundamentals. They have already read the fundamentals. For them it is not difficult for you to understand. But as you grow up, you see that in Lewis, this is the limitations are there. Got it? So according to Lewis, all negatively charged species, F minus, Cl minus, Br minus, I minus, OH minus, then the substances which contains this lone pair, they are also electron donor, isn't it? Like ammonia, like water, 2 lone pair, like ether, ROR, like amines, RNH2, nitrogen, we can say that. So all these are considered to be as Lewis bases. All these are, so many you will be getting, so many I said you know, so many. All negatively charged radicals and the species which contains a pair of electrons, at least one pair. Here you can see 2 pairs is also there. At least one pair, like here one pair, here one pair. So they are considered to be as Lewis bases. And the one which has got deficiency of electrons means the one which is positively charged species, and which has got deficiency of electrons in its outermost shell, means which does not obey the octet rule, which have got less than 8 electrons in the outermost shell, like AlCl3. You have studied in chemical bonding. I have studied. Like AlBr3, BF3, BEF2. Got it? So those particular substances which do not have octet in their outermost shell, like AlBr3, AlCl3, FeCl3, we can say that, then BF3, then boron trichloride, BCl3, got it, BeCl2, beryllium chloride, got it. All these substances are considered to be as Lewis acids because they have deficiency of electrons in their outermost shell. So neutral substances which have got deficiency, got it, and positively charged species are known as Lewis acids. And neutral substances which have got lone pair of electrons and which are negatively charged species are known as, what you can say, Lewis bases. I hope it is clear to you what are Lewis acids and Lewis bases and what are the limitations that also I have told you. Now next is your ionization constant of acids and bases. Already I have discussed with you ionization constant of acids and bases. For acid the ionization constant is Ka and for the base it is Kb. We can say that. Clear? So Ka stands for acid dissociation constant and Kb stands for the base dissociation constant. Similarly, if you are having large number of acids and bases, if you are having, got it, and if you want to measure its strength, we can say that. Got it? Like suppose we are having 2 acids whose dissociation constant, one is Ka1, another is Ka2. Got it? Ka1 and Ka2. So strength of the acid 1 by strength of the acid 2 is equal to root over of Ka1 by Ka2. Let me write it down. Clear what I said? Strength of the acid 1 by strength of the acid 2. What I said? Strength of the acid 1 by strength of acid 2 is equal to root over of Ka1 by Ka2. Similarly, if it's a base, acid 1 means Ha1 also you can say, and acid 2 means Ha2 also you can say, because I said you, in general for acid we use Ha symbol. Similarly, for the base, strength of the base 1 by strength of the base 2 means strength of BOH1 by strength of BOH2 is equal to root over of Kb1 by Kb2. We can say that. Clear? In this way, if one is unknown to you, anyone is unknown to you, you can measure it, you can find it out by using this formula. Got it? Clear? Similarly, if an acid dissociates to a number of steps, like suppose we are having tribasic acid, like H3PO4, it will dissociate in 3 steps. H3PO4. First, one H plus ion will be released in the first step. In the second step, second H plus ion will be released. In the third step, third H plus ion will be released. Isn't it? For example, NaOH reacts with H3PO4. Will give you NaH2PO4. Got it? Clear? Now, in the second step, it will be Na2HPO4. In the